Suppose we're building a 2D pirate-themed combat game. Players can steer their ships through open waters and duel with other players they encounter. We want to implement an attack by firing a cannon from the port side, or the ship's left side when facing forward. However, our game currently only defines the ship's forward direction. From this vector, how can we compute a direction vector that points straight out from the ship's port side? A key observation is that the ship's forward direction and the direction the cannon fires should be independent. A shot fired straight out the side of the ship shouldn't have any forward or backward component. In math terms, these two directions are orthogonal. You can think of this as the ship having its own local coordinate system, a forward axis and a sideways axis, analogous to the world space x and y axes, but rotated to match the ship's orientation. If you've seen my dot product video, you'll know that the dot product measures how much one vector points in the direction of another. Since we want to find a vector v that is completely independent of the ship's forward direction u, its projection onto u must be 0. Or in other words, their dot products must be 0. A simple way to satisfy this equation is to choose the components of v so that the two terms cancel each other out. We can achieve this by swapping the components of u and negating one of them, producing a family of solutions in this form, where lambda is any scalar value. And we can verify this like so. Setting lambda equal to 1 gives a direction pointing out from the ship's port side. If we also want to support firing from starboard, or the right side of the ship when facing forward, we can just use lambda equal to -1. Now that we have the sideways firing direction, we can implement the cannon mechanic. Now we have a revelation that our game is better off set in outer space and in 3D, giving our pirate ships more freedom of movement. Let's see how this affects our cannon firing mechanism. For a forward direction u, we want to find a direction vector v such that its dot product with u is 0. Unfortunately, this equation alone doesn't narrow things down enough. Any vector orthogonal to u satisfies this constraint. Geometrically, these vectors form an entire plane perpendicular to u. But we don't want our cannons to fire in any arbitrary direction within that plane. We want a single direction that points directly off the side of the ship, with no upward or downward component. To narrow it down further, we need an additional constraint. We can get one from the ship's up direction, represented by a vector w, which will store alongside its forward vector. Intuitively, the firing direction off the side of the ship should be perpendicular to both the ship's forward direction and its up direction. In other words, we're looking for vectors v that are orthogonal to both u and w. There's a standard operation that produces a vector perpendicular to two others in 3D called the cross product. The cross product of the ship's up direction w and its forward direction u is defined as this. And we can verify this vector satisfies both of our dot product constraints, which I'll leave as an exercise to you. As in the 2D case, this solution isn't unique for our orthogonality constraints. Multiplying the result by any scalar produces another vector that remains orthogonal to both u and w. Choosing a value of 1 for lambda gives a direction vector pointing off the ship's port side, while -1 flips the direction to the starboard side. The magnitude of a cross product also carries useful meaning. For now, we're only interested in its direction, but we'll return to the significance of its length in a later example. To understand which direction a cross product points visually, we need to know the handedness of the coordinate system we're working in, or how its world space axes are oriented relative to each other. A coordinate system can be either right-handed or left-handed, depending on that orientation. This choice is a convention set by the game engine. For example, the Godot engine uses a right-handed world space, but Unity uses a left-handed one. In a right-handed system, the direction of a cross product follows the right-hand rule. For vectors u and v, point your right hand in the direction of u and curl your fingers towards v. Your thumb will then point in the direction of u cross v. In a left-handed system, the same visualization applies using the left-hand rule. It's worth noting that the algebraic definition of the cross product does not change between right and left-handed systems. What changes is how that result is interpreted geometrically based on the orientation of the coordinate system's world space axes. One way to determine a system's handedness is to check which hand satisfies the relation z is equal to x cross y, where x, y, and z are the engine's world space axes. Another property of the cross product is that it is anti-commutative, meaning that swapping the operands negates the result. We can see this effect directly in the pirate ship example. Knowing we're in a right-handed world space coordinate system, use the right-hand rule to determine the direction of v equal to w cross u. Now repeat the same process for u cross w. You should find that the result points in the direction of -v. There's another canonical equation that relates the magnitude of a cross product to its two operands. While it's not often used explicitly in everyday game code, understanding it can still be very useful. We won't derive it in this video, but I'll link an example derivation of it in the description if you're interested. Here, theta is the angle between vectors a and b. In our space pirate example, the ship's forward and up directions are perpendicular, so theta is equal to 90 degrees between w and u. In this case, the magnitude of the cross product between w and u is just equal to the length of w times the length of u. This means that if w and u are kept to unit length, their cross product is also of unit length. Keeping direction vectors normalized like this is a common practice and helps keep the math well behaved. Now let's consider more general situations where the angle between the vectors differs from 90 degrees. In these cases, the sine theta term becomes significant, and the angle between the vectors can carry real physical meaning. One important example of this is torque. In physics, torque describes the tendency of a force to cause rotation. It's defined as the cross product of a position vector from an object center of mass to a point of application of the force, and the force vector itself. Implementing a full torque-based physics system is outside the scope of this video, but the geometric meaning of this definition is easy to see in practice. Let's take a look at an example. We'll set up an object that's fixed in place but free to rotate when a force is applied. When the object's clicked, a force is applied at the point of contact. The force vector points in the direction of the applied force, while the radius vector points from the object's center of mass to the contact point. The resulting torque vector represents the axis of rotation, and its magnitude determines how strongly the object rotates. From the torque equation, we can see there are three ways to increase the torque applied to an object. We can increase the amount of applied force, we can increase the distance from the center of mass, or we can make the force and radius vectors as close to perpendicular as possible. Notice how the object barely rotates when the line of action of the force nearly passes through the center of mass. The cross product is only formally defined in 3 dimensions. However, the underlying idea of orthogonality applies in any number of dimensions, as we saw earlier in the 2D example. In practice, when game devs refer to a 2D cross product, they usually mean taking the cross product of two 2D vectors with an implicit third component of 0. This produces a 3D vector pointing straight out of the screen or into the screen, depending on the orientation of the vectors and the coordinate system's handedness. In 2D games, only the z component of the cross product is typically used. We'll close with a more advanced example by implementing a ray triangle intersection test in 3D. This example puts both the cross product and the dot product to work in a concrete, real-world game dev scenario. If you're not already comfortable with the dot product and its geometric meaning, feel free to check out my other video. Suppose we want to fire a laser straight off the bow of the ship in its forward direction. Let's define a data type that represents the position and the direction of the laser when it's fired. We'll assume the direction is normalized, which simplifies the math later on. In most game engines, complex geometry is represented as a mesh of triangles. We'll assume each entity exposes its geometry as an iterator over triangles in world space. The winding order of the triangles is important here, and typically follows a convention enforced by the game engine. We'll see the importance of this in a bit. Now we can loop over all the triangles in the scene and test each one for intersection with the ray. For each hit, we record the intersection point and the index of the intersected entity, keeping only the one closest to the ray's source. In a real game, you'll probably want to reduce the number of triangles that need to be checked using some sort of spatial data structure, but this approach is sufficient for showing the math. The core of our implementation lives in the cast ray function. First, we compute the triangle's normal vector, or the vector perpendicular to its surface, as the cross product of two of its edges. This is where the triangle's winding order becomes important. Reversing the winding negates the normal, which would affect all our subsequent calculations. The handedness of the coordinate system also matters. Throughout this example, we'll assume a right-handed coordinate system, so the cross product follows the right-hand rule. We want a unit-length normal vector that points outward from the triangle's front face. Next, we check how the ray is aligned with the triangle's normal. Since both vectors are unit length, their dot product gives the cosine of the angle between them. If the value of this is 0 or negative, the ray is either parallel to the triangle or pointing towards its back face, so we can just return early. We can now compute how far along the ray needs to travel to intersect the plane containing the triangle. The point V0 is chosen arbitrarily for this. Any point on the triangle would yield the same result. By checking if the distance along the ray is less than or equal to 0, this prevents an edge case where an intersection could occur behind the ray's source. Finally, we only return the intersection point if it actually lies within the bounds of the triangle. We do this by checking whether the intersection point lies on the correct side of each of the triangle's edges. The winding order of the triangle matters here as well. With all this in place, we have enough to fire the laser cannon. Thank you so much for watching. Don't forget to subscribe and let me know if you have any questions or feedback in the comments.